Hi there, my name is Taebyn, I'm a pup, bark bark, and welcome to another Math with Taebyn. Today, I want to talk about and give you some examples of using double integrals in multivariable calculus. Okay, so double integrals in multivariable calculus. I'm going to assume that you know some things, such as what multivariable functions are, what the volume is in terms of double integrals. You know, you're integrating under your function of two variables. How to set up double integrals over rectangular regions. And again, just to review, you're integrating and your limits of integration are just the endpoints of the rectangles. So that makes it pretty easy in the case, rectangular case. And basic integration and U substitution. So something you have learned in your first integral calculus course. So I'm going to assume you know those because I want to focus on setting up and working with double integrals over non-rectangular regions. For me, here's the sentence I actually even write down when I'm trying to figure out limits of integration. Because you might have, if you've done this before, you might have noticed the hardest part is setting up the limits of integration, usually. So what helps me in determining this is I write down this sentence and fill in the blanks. For each x value, or maybe it's a y value, in a certain interval, the other variable, y, or maybe x, values go, that letter, y, equals something to something, or if you're talking about x values, x equals. So I want to do and write down an example of this. Here is our first example. Find the volume of the solid under this function. So it's like something, it's a function. Underneath that and above a certain region, and this region is bounded by these curves and these lines. We have, I'm just going to draw kind of a generic thing to remind you. We've got this function. You may know what it looks like, or you may not, but the point is just to know that it's this flowy Superman cape thing or something flying around up there. And then in the XY plane, you've got this region, which will look something like, something like this or something. So this is the region R. And then if you could imagine, you're looking for the volume of this, above this region R, you've got a kind of maybe a cylindrical looking thing or something, and you're looking for the volume of that. First thing to do is to identify this region R. What is it? That is essential to understand what R looks like, because that's what helps you put down your limits of integration. Our volume will be, it'll be double integral. You will have to fill in these question marks. So it's the volume underneath this function, xy, with respect to some letter and with respect to another letter. It doesn't really, sometimes it matters which order you do, sometimes it doesn't. In my next example, I'll talk a little bit about that. But let's do it with respect to y and then with respect to x. And then that tells you that, once you write that down, that tells you that the outer integral refers to x values, and then the inner integral refers to y values. Now let's write down that sentence that I talked about. For each, I go outside in, so for each x value in some interval that I'm going to figure out what that is in a minute. Fill that in a second. The y values go, and just to specify, I need y equals, I'm going to fill that in a second, to something. In order to fill in these blanks, I have to know what this region R looks like. So let's look at what this region looks like. Okay, draw my little axes. I have the line y equals 1/2 x, That looks about something like that. And then I have y equals the square root of x. So that looks something like that. And then I have the line x equals 2 and x equals 4. Well, notice x equals 4, that's actually the intersection of these two, right? Because x equals 4 in both of these gives you the same y value. So here's x equals 4, and then x equals 2 will be about here. And then this is your region R that you're integrating over. That's this. For each x value in where? Well, your x values go from 2 to 4. You're pulling your x values from this interval. That's where your region is. So 2 to 4. This tells you then what these outer limits of integration are. I'll write those down in a minute. The y values go, well, I actually even draw the arrow I'm going to write right now. The x values go from here, this line, up to that curve. So the x values go from down here, y equals 1/2 x, up to y equals the square root of x, the curve. So then we can write down the limits of integration. You get the x values are from 2 to 4, and, bark, the y values, remember that's the inner one because that's dy is on the inside, the y values go, just write down what you wrote in your sentence, 1/2 x up to y equals square root of x, dy dx. Then once you have that set up, of course, you just integrate. And as I said, I'm assuming you know how to just do the integration. Nothing funny or fancy, you just integrate. It's a pretty easy integration here. Just make sure you can do it. But if you do, you compute that, you would get 11. But that's the hard part, is setting up those limits of integration. So I hope that made sense. So let's move on to one more example. This example will actually have a lot of the exact same ideas as in the previous example, and a lot of these problems have the same ideas. So it's kind of good to understand these two basic examples because the ideas come up again and again when you do these sorts of problems. We want to evaluate this double integral, and you might be thinking, well, Taebyn, it sure looks like an easy double integral like you had us do in the last example, but actually, the problem here is integrating e to the x squared with respect to x. There is no techniques in your basic integral calculus class you learned that will help you integrate that. Like you can't do it like with those techniques. There's no antiderivative of e to the x squared that you would have learned it. In other words, the idea, let me write down the idea, is to switch the order of, that's a D, of integration. This stuff is fun. I always enjoy doing this stuff. But I'm a creep. And you'll see why that will help. You'll see why, but let me just basically explain why that's going to help. When you switch the order of integration from 2 dy dx, integrating the ex to the x squared, that's just like a constant now, because you're not integrating with respect to x. You'll just get a y e to the x squared, and it's nice and easy. You'll see, we'll do it, we'll see, but that's the basic idea. So, we want to take this guy that we're given, 0 up to 2, integral 1/2 y up to 1, and we've got e to the x squared, dx dy, and we want to switch the order of integration. Now, let me caution you. When people are first doing this, a lot of mistakes that people make is to just simply switch the limits. So they would put like a 1/2 y and a 1, and on the inner they would put a 0 and a 2. It unfortunately doesn't work that simply. It's because when you switch the order of integration, you're actually changing how you're describing the region that you're integrating over. So we'll see that in just a second. So I'm going to, for now, put question marks, because those are question marks we have to fill in. once we've got those question marks filled in, we'll pretty much be home free. We're still integrating e to the x squared, and we're switching the order to dy dx. Switching the order, right? So we're going to integrate with respect to y first. Okay, now we have to identify this region we're integrating over. What are we integrating over? Remember, like from the last example, I noted that dy is on the outside, so that means that the outer integral refers to y values. Y equals 0 up to y equals 2. The inner integral refers to x values. X equals 1/2 y up to x equals 1. So this helps us identify what our region looks like. So let's look at that. Okay, so let's write down that sentence. What do these limits tell me? They tell me for each, like I said in the last example, I go outside in. For each, outside is y values. Y values, because we gotta have values. For each y in the interval 0 to 2, the x values. So as I keep saying, I think it's really important to be able to write down this sentence, because they'll tell you, once you can do this, the rest of things just follow. The x values go x equals. I think it's important to write down x equals to remind yourself what letters you're talking about. X equals 1/2 y to x equals 1. This sentence helps us identify our region. The y values go from 0 to 2. So here's, say, 2 up here. I'm picking a y value from that interval. Now, the x values go, let's look at what x equals 1/2 y looks like. Well, we're used to writing things in terms of y equals, so if we were to solve y equals 2x, and that's of course just x equals 1. So if I draw y equals 2x, it looks about like that. And then y equals 2 is here. And then x equals 1 will be right here, right? Because that's the intersection point, actually, of when y equals 2 on this line. So it actually, the corners match up nice. But, so there's x equals 1. And the y values go from, and again, like I said before, I actually, when I do these problems, I write down this arrow to help me identify, is it the left side or the right side triangle? That's the region. Well, if you draw the arrows, it helps to identify. For each one of these y values, we go from the line to x equals 1. So we go from the line to x equals 1. That's for each x value. So that means this colored in space, that's our region R. And then, okay, now we're good, because now we're in the same situation as the last example. We can now fill in these question marks, because on this same picture, so the outer limits that we're looking for are x values. So x values, x equals something, and the inner are y equals something. So fill in those question marks. So just like the thinking before, start on the outside. The x values now are from what? The x values are taken from this interval from 0 to 1. So for each x value, I'll write down this sentence again then. For this guy, for each x in, now we're looking at 0 to 1, where do the y values go? Y goes, y equals what to what? Well, for each, here's an x value, and it goes from the x-axis. That's y equals 0. So you go from 0 up to this line. So you go from y equals 0 up to the line. It's not 1/2 y like before. We want x equals. That's why I write that in. X equals here on the outside, y equals here on the inside. So now we want y equals 2x, not x equals 1/2 y. So then We've got our sentence, then we can fill in these. X goes from 0 to 1, and y goes from 0 to 2x. And then you can integrate this. And I won't do the whole thing, but now I want to show you how this helped us. I mean, you can try doing that on your own now, which I encourage you to do, and maybe you'll see for yourself. We're looking at the integral from 0 to 1. If I integrate this with respect to y, there's no y in e to the x squared, so that's viewed as a constant. So this turns into y e to the x squared. This goes back to the whole, I'm assuming you understand basic integration to do this, but y equals x squared from y equals 0. Again, to remind myself what my letters are, y equals 0 up to y equals 2x. And then you plug those in and you get, well, if you plug in 0, you get nothing. So you've just got 2x x e to the x squared dx. And that's a basic u substitution, right? So that's something I hope you can do, but you would use the substitution u equals x squared will get you get e minus 1 as your answer. The main thing was switching the orders of integration and being able to draw your region. And you've really got to be able to do that, even if it's not precise. You just got to know some intersection points and be able to visualize something in order to write down your limits of integration. Well, so that was great. That was fun. I hope that helped you out very much. You just got to try problems and practice and stuff, and you'll find that it becomes more natural and easier, and you start realizing and seeing the ideas more and more. I hope to have fun with you then on our next adventures in math with Taebyn. Bark, bark.